Okay, here we go. We're going to look at the review that you guys have for your upcoming test on exponentials and logarithms. It starts off with a couple of definitions. I don't know if these are the best definitions that you can find, but if you don't like mine, you can always Google them or look them up in your notes. Common log. The common logarithm is a logarithm that's base 10. So when you take the base 10 log of a number, you're trying to say 10 to what power is that number? E, sometimes referred to as Euler's number, which is an irrational number. It's approximately 2.718. Is used in both the natural exponential functions, that's like e to the x, f of x equals e to the x, and the natural logarithmic functions, that's that ln. So a natural exponential function might look like f of x equals e to the x, and a natural logarithm function would look like maybe g of x is equal to the natural log of x. Because the natural log means log base e, base e. Then you had some short answers. I don't know how short these are, but for problem number 3, it says, what do we use a logarithm for? Well, when I was a student, because I'm old, I used to use them for calculations because multiplication became addition, division became subtraction, and raising a number to a power became multiplying by a scalar. This is back before the calculators came out and were affordable. Now, of course, we've got the calculators do all that work for us. We can use them, I think, probably one of the more common things, besides some of the different kinds of applications that involve logarithms, such as the Richter scale, decibels, things like that, determining how many decimals a sound is that we can use them to find what power to which we raise a base would be, to which a base would be raised to equal a given value. So again, if I said I have 5 to the x is equal, or actually I have one written right here. If I say 3 to the x is equal to 5, and I'm trying to figure out 3 to what power is 5, well, that power is called the logarithm base 3 of 5. Remember how to go from this form to this form and this form to this form. The base of the exponent is the base of the logarithm. These are equivalent expressions. Alright? Better know that one. Alright, not so much the short answer or the definition or whatever, but you better know how to go from this form to this form, from exponential to logarithmic to exponential. Alright, now, it says something along the lines of, how would you write 4 to the x equals 10 in a logarithmic form? Well, 4 to the x equals 10 is kind of like this one. I would change it into a logarithm. Now, I don't have a base 4 number. If I did, if I had a base 4 logarithm button on my calculator, I would say here that x is equal to log base 4 of 10, just like I did from here to here. But if I actually want to find x, I'm going to take the common log or the natural log of both sides, like I did here, and then I'm going to use that power property for logarithms to bring the exponent out in front, and then of course the log base 10 is the common log of 10 is 1. Remember, 10 to what power is 10? Well, that'd be 1. And then I would divide both sides by the log of 4. So if they want it written without the ability to grab your calculator, you could write it this way. If they wanted it written so that you could use your calculator, it would be this way. Again, notice the importance to be able to go from exponential form to logarithmic form and vice versa. Now, it doesn't do me much good on the calculator, again, because it's base 4. I can show you how to do that using base 10 or base E, where you can use your calculator. The change of base formula says that if you have base b logarithm, b being a positive number not equal to 1, you can write it to any other base greater than 0 not equal to 1. I have base a by writing this expression as the log base a of m, all divided by, now this is not a subtraction kind of a property, this is divided by the log base a of b. Now I see m being higher up than b is. B is a subscript. So notice the m goes on the top, the b goes on the bottom. Everything else is the same. Need to know that. And now I'm going to show you how to evaluate these 4 examples here. Now I'm better off if I think of this in terms of equaling some number x. So the log base 4 of 64 is x. This is the same. 4 to what power is 64? I see that better by rewriting it by setting it equal to x, rewriting it into exponential form, base 4, logarithm, base 4 exponent. There's my exponent x. And then I write 64 if I can as 4 to a power. Well, as it turns out, 64 is 4 times 4 times 4. So if 4 to the third equals 4 to the x, that means x equals 3. That means this expression is 3. Now again, it's saying 4 to what power is 64. That's what this means. 4 to what power is 64? 4 to the third power. So this is equal to 3. This is saying 6 to what power is 136. So again, you can't sit there and think of it in your head. Set it equal to x. Convert it from logarithmic form to exponential form. So I get 1 over 36 equals 6 to the x. Now 1 over 36, can I write it as 6 to a power? Well, 36 is now 1 over 6 squared. 136 is 1 over 6 squared. And here's one of the things that students sometimes forget. 1 over 6 to the second power means 6 to the negative 2. Remember your negative exponents. They're going to be used in this test. Now, just like this one here, if 6 to the negative 2 is equal to 6 to the exponents must be equal. X must be negative 2. This thing must be negative 2. 2 more to go. Again, 4 to what power is 2? Well, I don't know. Let's call it x. Let's convert this from logarithmic form to exponential form. So this comes on over and bumps the x right up as the exponent. And I get 2 equals 4 to the x power. Now, 2 is 2 to the first. 4 can be written as a power of 2. This time it's the other way around. The base I'm going to match here. So this is the base of the exponent I'm going to match here. So this is 2 squared. 4 is 2 times 2, and all that's raised to the x power. So that means 2 is raised here on the right. Multiply power to power, multiply the exponents. That's a 1. So if these are equal, the exponents are equal. 2x must be 1. X must be a half. Yeah, 4 to the half power is 2, because half power means the square root of 4, which we know is 2. So this is equal to 1/2. Over here, a little bit trickier, not that terrible bad, but a little bit trickier. I'm going to again call it x, and I'm going to rewrite this. I'll bring this over. I'm going to write 16 equals 64 to the x. Now fortunately, even though I can't write 64 as a power of 16 or 16 as a power of 64, conveniently, these are both powers of 4. This is 4 squared, and this is 4 to the third power. That's all being raised to the x power. So 4 squared equals 4 to the 3x. That means if the bases are the same, the exponents must be equal. 3x must be 2. X equals 2/3. So this thing here is equal to 2/3. And I have my... So I don't see a lot of people sitting there and think, oh, okay, 64 to what power is 16? Because it's a little tricky. I mean, if you really do a lot of these, you probably can figure them out, not too bad. But in this case, if you're a little new to this, just set it equal to x, change it to exponential form, match the bases, set the exponents equal, and then solve for x, and then make sure you answer the problem. Okay? Now, you have these properties of logarithms that allows you to condense and expand expressions. Now, I didn't write the properties down, but I'm going to erase this so that I can write the properties down and refer to them if I need to when I'm doing problems 10 and 11 here. So the three key properties, sometimes they're called the laws of logarithms. One, that the log base b of m plus the log base b of n is equal to the log base b of m times n. The second one, the log base b of m minus the log base b of n is equal to the log base b of m divided by n. And the third one, which is used quite a bit, the log base b of m raised to some power, let's call it k, is equal to k times the log base b of m. It's as if the exponent comes out in front. Or if the constant's out in front, you can bring it up as an exponent. And the fourth law of logarithms, which doesn't get as much praise, but I used it a little bit already, says that, actually I'm going to be using it in just a little bit, that says that if log base b of m equals log base b of n, this is true if and only if. IFF means if and only if m equals n. And of course, m equals n, they would have to be positive numbers. B would be a positive number not equal to 1. So now I am going to use this property and this property to expand this next problem, problem number 10. Because I have a quotient. I have the log of a quotient. Look right here. I have the log of a quotient. So this is equal to the log of the numerator minus the log of the denominator. So this is equal to the log of the numerator minus the log of the denominator. Now I can expand this just a little bit more. I don't know what the log of 3 is, but I can expand this by using the third property that says that if I have an exponent, I can bring it out in front as a constant factor. I have this exponent of 2. I can bring this 2 out in front, right? This is 2 times the log of x. Okay? Now you should be able to take a simple logarithm and expand it into sums and differences of logs, and vice versa. Here's the sum and difference of logs, and I'm going to condense it into a single logarithm. Now the first thing I do was the last thing I did here. I took care of the exponents. I'm going to take care of the exponents. There are no exponents, but yes there are, because I have constant factors in front of 2 of these. So I'm going to bring these up like this as exponents. I'm going to write this as the log of 3 squared, of course that's 9, plus the log of x minus the log of 27 to the 1/3. Now 27 to the 1/3, that's the cube root of 27, that's 3. So now I'm going to write this as the log of 9 plus the log of x minus the log of 3. Now I'm going to use property number 1 up here. I have a sum of 2 logs. I'm going to write it as the log of a product. So the first 2 here, this is going to give me the log of 9 times x minus the log of 3. Now I'm going to do the second property here and do this difference and write it as a quotient. Right here, the log of an expression minus the log of another expression is equal to the log of the quotient of those 2 expressions. M over n, in this case it's going to be 9x over 3. So this is going to equal here, I'll put it right here, hopefully you can see this, the log of 9x over 3. Now if you left it just like that, teacher might take something off on that because 9x over 3 does simplify. You can divide top and bottom by 3, and this is the log of 3x, and that would most likely get you full credit. Alright, now I've got a whole bunch of other problems, including some equations, and I'm going to run through these next. Now, I went through this information quite quickly. You're going to need to know pretty much everything we talked about, but then you're definitely going to be solving both the exponential equations, problems 12 and 13, and logarithmic equations, problems 14 and 15. Okay, and then we'll do a little bit more here with simplifying. I'm going to probably have to erase a little bit of this stuff down here to do problem number 12 because I didn't give myself very much space. I keep erasing stuff, but this is a video, so you can always rewind if you need to see it again. Alright, first things first. 4 to the x plus 1, 1/64. I look at this 4, I look at 64, I'm thinking 64 can be written as a power of 4. 4 to the x plus 1 is equal to 1 over 64 is 4 to the 3rd. 1 over 4 to the 3rd is the same as 4 to the negative 3. You're going to need to remember this. So now I have this is equal to this. See how the bases match? So the exponents must be equal. That means x plus 1 has to equal negative 3. Subtract 1 from both sides, and I'm going to get x is equal to negative 4 is my answer. I just subtracted 1 from both sides. I guess I didn't need to erase that after all. Here's another guy, and again, I looked at that 3 and that 27. I know 27 can be rewritten as 3 to a power, so I'm going to leave the left side the same. But 27 I'm going to write as 3 to the 3rd power, because 3 times 3 times 3 is 27, and all that's to the 3x. By the way, the paper I'm looking off of is very difficult to read. The print was very small. So if I have a different expression than what's on your paper, it's because it looks like this to me, and that might be a 2x for all I know, but I'm going to just go ahead and leave it as a 3x. If it's a 2x, make the adjustment. If this is x minus 1 instead of x minus 7, make the adjustment. But I'm going to go ahead and now write this, because that's a power to a power, you multiply the exponents. So 3 times 3x is 9x. The bases match just like they did back here. Set the exponents equal, set the exponents equal. Set x minus 7 equal to 9x. I'm going to subtract x from both sides. I get negative 7 equals 8x. I'm going to divide by 8. And I get x equals negative 7/8. And there's my answer there. At least I think that's the answer because I can't tell on some of this small print. Those are your exponential equations. We got one more, I think, that's coming up that we'll get to in just a little bit. Actually, I think there are two more that are kind of like what happens when you can't match the bases. When you can match the bases, this is the route you go. When you can't match the bases, you use logarithms. Problem number 14 is a logarithmic equation because the variable is in the log expression. Just like these are exponential equations because the variable is in the exponent. So in this case, I'm going to isolate my logarithmic expression. There's just this single logarithmic expression, so I'm going to kind of solve around it just like I would a linear. I'll undo the plus 1 by subtracting 1 from both sides. Oh, there goes my pen. I get 3 times the log base 2 of x is equal to 7 minus 1 is 6. Then I'm going to divide both sides by 3, and I get log base 2 of x is equal to 2. Now, I'm going to change this form, logarithmic form, into equivalent exponential form. Let me write it over here to make sure you remember how to do this. Log base b of m is equal to k if and only if m equals b raised to the k power. If and only if. Work either way. So what I have here is I'm going to change this into exponential form by bringing this base over as the base for the exponent, and I get x equals 2 squared. That's this 2 here, that's this 2 here as the exponent. Of course, 2 squared is 4. There's my answer. Now, on logarithmic equations, be careful because if you get an answer and you plug it back in, and it gives you the logarithm of a negative number, that answer is no good. It's extraneous, and you got to toss it. That answer is okay. In this case over here, I have 2 logarithms, so I can't isolate a single logarithm like I did here. But what I am going to do is I'm going to get the logarithms on the same side. I have this third term. Now, if that plus 1 wasn't there, I just set the expressions equal to one another. I'd set the 2x minus 1 equal to 5x. But because of that plus 1, I mean, if that wasn't there, it'd be easy. Set these equal. That'd be this property right here. But because of this plus 1, I can't do that. I am going to subtract the log of 2x minus 1 from both sides. It's going to make it a little bit of a pain. These are going to cancel. I'm going to get 1 equals, and then over here, I've got the log of 5x minus the log of 2x minus 1. Well, these are common logs, and you have a difference. I want this as a single log, so I'm going to use this property right here, property number 2, and I'm going to write the right side here as the log base 10, this is a common log, of 5x all over 2x minus 1. Well, talk about needing extra space. Now, I have this, kind of like I had this. I'm going to change this into exponential form. This is a base 10 logarithm. I'm going to bring the 10 over as the exponent. I get 10 to the first equals 5x over 2x minus 1. And I'm starting to run out of space, but I'm going to try to squeeze it in. I now have, that's to the first power, so I don't really need that anymore. I'm going to change this. This is a rational equation. I'm going to change this into just a traditional equation by getting rid of the denominator. One way to do that is to cross multiply or multiply both sides by the LCD. So I get 10 over here now. 10 times the quantity 2x minus 1 equals 1 times 5x. I get 20x minus 10 is equal to 5x. I'll subtract 20x from both sides. I'm really running out of space. And I get negative 10 equals negative 15x. I'm going to divide by negative 15 on both sides. And if you can still see it, I'm going to get x equals negative 10 divided by negative 15 is positive 2/3. Now if I go back here and I put 2/3 in here, 2 times 2/3 is 4/3 minus 1 is 1/3. It's still positive. And 2/3 here, that would be 10/3. That's positive. So this is a good, legitimate answer. That's 2 over 3 there. I know it looks a little like a 5, but that's a 3. All right, on problems 16, 17, and 18, they give you some information in the directions. They tell you approximations for the log base 2 of 3 and the log base 2 of 5, and they want you to approximate these. They don't want you to get the change of base formula working here. They want you to approximate these. And this is where you're going to use these properties. Now look at the two logs that you have. You have the log of 3 and the log of 5. I look at 15 and I'm thinking 3 times 5. This is the log base 2 of 3 times 5. And then using the first property here, this is the log base 2 of 3 plus the log base 2 of 5. Now I have both of these approximations. This is 1.58 and this is 2.32 if I'm not mistaken. And that adds up to 3.90 or just 3.9. And that would be my approximation. That kind of makes sense. Now 2 to the 4th power is 16. So 2 to what power is 15? It'd have to be a little less than 4. Alright, let's try another one here. Now I have a 5, which is great because I have one of the logs with the 5 in the directions. I don't have the 1, but remember this. Log base b of 1, any base, positive number, greater than 0, positive number, not equal to 1, this is always equal to 0. B to the 0 is 1. Any base to the 0 is 1. So if I write this using property 2, I would have log base 2 of 1 minus log base 2 of 5. Well, I just said that any base log of 1 is 0, so this is 0, minus the log base 2 of 5, which I said a little bit ago was 2.32. So 0 minus 2.32 is negative 2.32. That is 0 there, but I don't think you need it anymore. Alright, now I got a little bit of fun here. I have a log base 2 of 50. Now, I can see 5 divides into 50. In fact, 5 divides into 50 10 times, and 10 is divisible by 5. But I'm going to get a factor that maybe I'm not too sure about using because I don't have it in my directions. I'm going to think of this as the log base 2 of 2 times 5 times 5. Because that's 25 times 2 is 50. So this is the log base 2 of 2 plus the log base 2 of 5 plus the log base 2 of 5 again. Now I could have done the exponent thing, but that's fine. These two I have. I just said it, about 2.32. But what's the log base 2 of 2? Well, this is not a property per se, but it should be a property. The log base b of b, when these match, it's 1 because it's the same. This to what power is this? Is itself. B to the first is itself. So log base 2 of 2 is 1. Plus 2.32 plus 2.32. So that's approximately what? 5.64. Okay, now we're having some fun. And notice how often I refer back to these properties. You got to know them, you got to memorize them. Now I'm going to do a sketch, and I'm not crazy about sketching log functions. And in fact, I'm going to erase some, maybe I can squeeze some of this in here. Let's see. I'll erase this as well up here. I'll erase all this for right now. Okay, I'm telling you, on these kinds of problems, you're better off thinking of this by thinking of it as the parent function. Forget the minus 2, forget the plus 3. The minus 2 shifts it right 2 units. The plus 3 shifts it upward, because it's positive 3 units. Remember, it's in the form x minus the number. If this was x plus 2, it'd go to the left 2 units. Kind of the opposite of what it looks like inside, exactly what it looks like outside. But if I start with this, and again, I'm not good at plugging in numbers for x here, I'm going to convert it into exponential form. So I would get x is equal to 2 to the y. I would create a table of values, x and y, and I would plug in some numbers, not for x, but in for y, because it's easier to take this and figure out what x is. I'm thinking negative 2, negative 1, 0, 1, and 2. 2 to the negative 2 is 1 over 2 to the second. 2 to the negative 2 is 1 over 2 to the second. That's 1/4. So the x value is 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. Remember, 2 to any number raised to the 0, any non-zero number raised to the 0 is 1. 2 to the first is 2. 2 to the second is 4. Well, what happened? Remember I said it's going to go right 2, up 3. So let's do this again. Right 2 means I'm going to add 2 to each one of these. So that's 2 and 1/4. That's 2 and 1/2. That's 3. That's 4. That's 5. Oh, that's 6, if I can add. And then 3 up means I'm going to add 3 to each one of these. So that'd be 1, that'd be 2, that'd be 3, that'd be 4, and that'd be 5. I'm going to graph those. Now, let's go back. This number here that you're taking the logarithm of, x minus 2, whatever this is, this has to be positive. X minus 2 has to be positive, which means x has to be greater than 2. If I add 2 to both sides. I've got a vertical asymptote at x equals 2. Everything's going to be to the right of x equals 2 when I graph this. So, hopefully you'll be able to see my graph. My pen is certainly starting to let me down here. Okay, so I have x equals 2 as my vertical asymptote. If you draw it in, and it probably wouldn't kill you to, make sure you make it dotted. All right, now I'm going to plot these 5 points, and I know the basic shape of a log. Okay, it's kind of a curve that kind of goes up like this, kind of goes up and to the right, goes definitely down, and approaches the vertical asymptote. So 2 and 1/4, 1. 2 and 1/2, 2, 3, 3, 4, 4, and 6, 5. 1, 2, 3, 4, 5, 6, 5. 2, 3, 4, 5, 6, 5 up here. You see the curve? It's going to come down and get closer and closer and closer and never touch it. And it's going to go up and to the right very slowly after a while. And that's your graph. Flat out memorize it. I'm going to tell you, if he has one on the review, he's not doing that just to keep you honest. He's doing that because he plans on doing one of these come test time. All right, let's see if we can squeeze a couple more in before I have to erase the board here. All right, it says which expression is equivalent, this is number 20, is equivalent to log base, looks like 3 of 64. Well, there's a couple different ways to do this, but an equivalent expression like this most likely means they're writing it in exponential form. Well, if I do that, then I have to introduce a variable. Well, that's no good. I don't want to introduce a variable because there's no variable in any of these answers. So then I started thinking, all right, it's a base 3 logarithm. Now I've erased it, but what about if we used the change of base? I noticed that all my answers, the logarithms, are base 10. Let's write this as the common log of the top part divided by the common log of the bottom part. And to me that looks a whole lot like answer D. Okay? So I went from here to here. Now remember, on multiple choice, look at the answers and see if they give you any insight on how they go about to change it. Problem number 21. This one is a solve for x. In 21, they say that the natural log of 2x minus 1 is 2. Well, the only way you're going to solve a logarithmic equation is either match the bases, this is base e, this is base 2, you're not matching them, or convert it from logarithmic to exponential form. This guy back here. Remember, it's base e, so the e comes over and I get 2x minus 1 equals e squared. I'm going to add 1 to both sides because I don't have a calculator handy enough to go ahead and figure out e squared. I know it's like a little less than 9, 8 probably something. So this is e squared plus 1. Then I divide by 2 to solve for x. And I get x equals e squared plus 1 divided by 2. Now notice that answer D looks just like that. So even though I could have gotten a calculator. It wouldn't have helped me on this one because they wanted to match the exact answer. There again, you look at the answers if it's multiple choice and kind of think about this in terms of what am I got to match up with. I'm not going to use a calculator. There's no decimals. All right, so that leaves, let's see, 3 equations and a story problem. Well, let's give it a shot. Let's just go ahead and continue with this video. I'm going to erase all this stuff best I can. I'm going to leave those properties on there in case I have to refer to them. I can't remember if I do or don't. Maybe not. But I'll just go ahead and see if I can solve these 3 equations here. Now it says round to the nearest 1,000, so that tells me right away I better grab a calculator. First thing I better grab is I better grab a pen that's got a little bit more juice to it. Let's see if this one works any better. So, problem number 22 here. Long video, I know, but you don't have to watch it all in one sitting. You can do it in parts. This is solving 3 to the x, looks like minus 3 is equal to 5. Okay, this is an exponential equation. It's an exponential equation because the variable is in the exponent. You can only solve these one of really 2 ways. One way is to match the bases. This is base 3, this is base 5. These are prime numbers. There's no way you can write 3 as 5 to a power or 5 as 3 to a power conveniently. We did that in the earlier problems. Problems like number 12 and number 13. In this case, we're going to have to use logarithms. We're going to have to use logarithms because we've got to get that variable out of the exponent. I can't solve it if the variable's up there. I need it down where I can get at it. So if I take the common log of both sides, and because these are positive, I can take the log of both sides, and then use property number 3. I guess I did use that one of the properties after all, and bring that exponent out in front. I get the variable where I can get at it. This is good. This is very good. Now I will have to distribute, and I get x log 3 minus 3 log 3 equals log of 5. I'm going to add, get the variable by itself. I'm going to try to get the variable all by itself. I got to get rid of the stuff around it. I'm going to add 3 log 3 to both sides. Now, think about this. Oops. 3 log 3 can be, this is log of 5, plus 3 log 3. I can bring the exponent up here. I would have the log of 3 to the third, which is 27. So now I have x times the log of 3 is equal to the log of 5 plus the log of 27. Now if I wanted to, I don't have to, because I can use my calculator here. If I wanted to, I could combine these using property 1. But since I'm trying to get x, why not just go ahead and take care of this by dividing both sides by the log of 3. Just be careful when you enter it into your calculator because you're adding a couple of logs here. Use your parentheses. And this is going to be approximately, I got this to be 4.46497. Now it says round it to the nearest 1,000. This is the 1,000 spot, so I look to the right. It's 5 or bigger. I'm going to round up. So my answer would be 4.465 to the nearest 1,000. Problem 23 says log base, looks like log base 2 of 3x plus 4 minus log base 2 of x plus 2 is equal to 5. Now, I know that your first attempt, I think you tried to subtract the logarithms. Remember what subtraction means when you're subtracting 2 logarithms. It means a quotient. This left side here, this is log base 2 of 3x plus 4 divided by x plus 2. You don't subtract them. And that equals 5. Now I don't know how to solve that because it's a logarithm, so I'm going to convert it to an equivalent exponential by bringing the 2 over as the base of the exponent, and I get 3x plus 4 over x plus 2 is equal to 2 to the 5th, which is 2 times 2 times 2 times 2 times 2, 32. So I have 3x plus 4 over x plus 2 is equal to 32. If you want, put it over 1. So now you can solve by cross multiplying I'm going to have to be careful here. 30x plus 4 times 1 is 3x plus 4. I'm going to distribute. 32x plus 64 is equal to 3x plus 4. And now I'm going to solve for x. It's easy now, but I'm going to check my answer to make sure I don't get anything weird. I think it's going to be okay. Just kind of looking at it. I subtract 3x from both sides. And I get 29x plus 64 is equal to 4. I get that right? Looks like I got that right. Now I'm going to subtract 64 from both sides. I get 29x is equal to negative 32. Oh, I don't like that negative. Divide both sides by 29. I am definitely going to check my answer. I don't want to end up with that. The next one. Now, by the way, if you punch this out on the calculator into 3 decimal places, I got negative 2.069. 3 times negative 2.069 would be a little bit like negative 6. Negative 6 plus 4. Uh-oh, there's a problem. I'm going to get the log of a negative number. This is no good. No solution, or empty set. My only possible answer makes this logarithm negative, makes this logarithm negative. You always check. All right, the last equation, see if I can squeeze them in over here. I don't think I'm going to be able to, but I'm too silly to erase it. So let's try 2 to the x plus 1. This is problem 24. Is equal to 5 to the x. Now, just like this guy here, I have an exponential equation. I actually have exponents in both, variables in both exponents, but I can't match the bases. This is a prime number, this is a different prime number. So just like I did over here, I'm going to take the log of both sides, and also just like I did over there, but on both sides this time, I'm going to bring the exponent out in front, using property number 3 again. So I have the quantity x plus 1 times the log of 2 is equal to x times the log of 5. I have to distribute. I did this before, so I get x log of 2 plus the log of 2 is equal to x log of 5. Now, I am going to get the variable, which is on both sides, on one side only. So this has got the extra term. I'm going to subtract x log 2 from both sides. I get the log of 2 is equal to x log 5 minus x log 2, the logarithm of 2. I have the variable written twice, but since it's in both, I can factor it out as a GCF. I got log of 2 is equal to x times the log of 5 minus the log of 2. I'm going to divide both sides now by this messy looking expression. Log of 5 minus the log of 2. Log of 5 minus the log of 2. These cancel out, and I get x equals this. Now, this is again where I have to grab my calculator and I have to be very careful not to enter my information in wrong. Now, when I did this, I got this to be 2.269 to 3 decimal places, to the nearest thousand. And if you plug that back in, you have no problems here. This is an exponential equation, not a logarithmic equation. That's a legitimate answer. And last but not least, the story problem. Now, here's another couple of things that you're going to need to know. You're going to need to know how to figure out compound interest. So you're going to have to memorize 2 formulas. Compound interest when it's compounded n times compounded, and when it's compounded continuously. Okay, if it's compounded n times a year, A equals the principal times the quantity of 1 plus the rate of interest, not written as a percent, but change it to a decimal, divided by n, the number of times it's compounded. It's like if it's compounded quarterly, n is 4, raised to the n times t. That's still the number of times it's compounded, and t is the number of years. So you multiply those, and that becomes the power. So do the stuff inside here, raise it to this power, and then whatever you get, multiply it times the original investment. If it's compounded continuously, it looks like PERT. P-E to the RT. Where that's your principal, that's Euler's number there, that's about 2.718 and so on. That's your rate of interest. Again, you'd write that as a decimal, and that's your time in years. In problem number 25, it says, find the amount that's accumulated after investing $4,800 for, is that 17? 17 years at an interest rate of 6.2% compounded quarterly, 4 times a year. I'm going to use this formula, not this one. Round to the nearest cent. So A equals $4,800. That's 1 plus 0.062. That's 6.2% as a decimal. Slide it 2 places to the left, drop the percent sign. Divided by 4, raised to the 4 times 17 power. 4,800. This turns out to be 1.0155. I divided and added 1, raised to the 68th power. I multiplied the exponents. Now, when I punch this into my calculator, I got 13,660.81. Now, it wasn't 0.81, but I rounded it to the hundredth because this is money, and that's the cents. So, how much was invested, or how much is accumulated? They accumulated, if I can spell this, accumulated. Don't forget your money, your dollar sign. $13,660.81. All right, now, I want you to make sure that you practice this and that you have your questions ready so you can ask me if you're unsure about any of this work or about any of these kinds of problems, because I'm guessing everything that's on this review, you're going to see it on the test. Good luck practicing.